Hello, ladies and gentlemen. Welcome to Physics 20 Kinematics Lesson 5, the Kinematics Equations Part 1. Now today we're going to explain qualitatively and quantitatively uniform and uniformly accelerated motion when provided with written descriptions, numerical and graphical data. Now, kinematics is the study of motion without much regard for what is causing the motion. Now we can develop three new equations for studying objects with a constant acceleration. All we need to do is substitute old equations to form new ones. So let's get recycling some new equations. Now, first thing, displacement from velocity in time and accelerated motion. During constant acceleration, velocity is changing, so we can no longer talk about plain old velocity in the equation displacement is velocity times time. The equation displacement is velocity times time only holds if there's no acceleration. But if we have acceleration, for problems with constant acceleration, we must use the average velocity, v average. Now, displacement from velocity in time, v average is 1/2 of v final plus v initial, where vf is v final and vi is v initial. Now recall displacement is velocity times time. Substitute equation 1 into equation 2, we get displacement is v final minus v initial times t divided by 2. Now that's often written 1/2 v final minus v initial times t. Right? Now, this equation makes sense if we consider velocity versus time graph. Consider a velocity versus time graph of constant acceleration. Recall the area under the graph gives displacement. The area under this graph forms a trapezoid. So v initial, v final, and time. And more specifically, we get a trapezoid like that. h1, h2, and b. So the area of a trapezoid is h1 plus h2 times b divided by 2. Or displacement is v final minus v initial times t, v final plus v initial, my bad, times t divided by 2. Note the formula for area of a trapezoid gives us the first kinematics equation. And something I'm going to stress here, back here, I forgot. Note, oh, you bokcha. This equation, and make a note of this, do not have or need acceleration. So that's a hint. We use this formula when we don't have or don't need acceleration. So let's try a question. A puma moves with a velocity. My apologies. With the velocity of 3 meters a second east and accelerates constantly. If the velocity after 4.70 seconds is 15 meters a second east, what is the displacement of the object, the puma? So, v initial, v final, acceleration, displacement, time. Make a list of everything you know. Now, v initial is 3.0 meters per second. Now, moving east, we'll call that positive direction. Accelerates constantly. We don't know v final. We know time is 4.70 seconds. And, oh, we do know v final. 15.0 meters a second. So, there's the puma. There's it moving east. So, displacement is 1/2 v final plus v initial times t. Yes, I forgot my vector arrows. Anyway, so displacement, 1/2, 15.0 meters a second, plus 3.0 meters a second, times 4.70 seconds. So displacement is 1/2 times 15 meters a second times 4.70 seconds. And I cannot do that in my head, so I'm grabbing Mr. Calculator. Clear, graph, clear. 0.5 times 18 times 4.7, 42.3 meters. east. All right, we see how that goes. And note, we don't need acceleration. Now, a driver accelerates constantly to a velocity of 7.5 meters a second during 4.5 seconds. The driver's displacement is 19 meters east. What's the final velocity? Well, once again, make a list of everything you know. V initial, V final, acceleration, displacement, and time. So, to a velocity. Okay, actually, there's a typo here. Another one. God help me, I'm getting old. The driver accelerated constantly to a velocity. What is the initial? I gave you the final velocity, so what's the initial? I apologize, ladies and gentlemen, I'm getting old. So, 7.5 meters per second. No, it's east. We're assuming he's always going east. The displacement is 19 meters, 4.5 seconds. We do not have, nor do we need acceleration. We need velocity, the initial. So there's the object, it's going east. Displacement, 1/2 v final plus v initial times t. So 19 meters, 7.5 meters a second, plus v initial, times time, which is 4.5 seconds. All right, now, here, this becomes an order of operations question. Once again, I'm doing this kind of fast. I'm expecting you to follow along and learn, not copy it out. If I'm going too fast, I don't want it to be that slow for you to copy it out, because many people are just watching this to learn. So, once again, pause the recording if I'm going too fast. So 19 meters equals 2.25 seconds times 7.5 meters a second plus v initial. Now, I would suggest, first things first, divide both sides by 2.25. And once again, I can't do that in my head. Oh, you bakcha. .44 seconds. Meters per second is 0.5 meters per second plus the initial. Now, some people would say, why don't you, Mr. Sutton, why don't you multiply it out? 2.25 times 7.5. That will give you an extra step, because right in here, all you have to do is subtract 7.5 meters per second from both sides, and you're down to the initial is minus 7.5, 0.94. Now, excuse me, 19 meters, 2.25 seconds. Really, sorry, the 7.5 limits me to the 1 decimal place, so this is 0.9 meters a second, or 0.9 meters per second east. Okay? Well, I hope you got it. Now, another thing you have to notice is displacement when acceleration, initial velocity, and time are known. Notice no v final. So sometimes problems will give us acceleration, time, v initial, but no v final, and sometimes there's no initial, but more on that later. But we can still solve for d. First, we must combine two equations from the past. Now, note, I don't expect you to be able to derive these. I expect you to be able to look them on a formula sheet and use them. Displacement is 1/2 v final plus v initial times t, but we don't have v final, so recall acceleration is v final minus v initial divided by t. Therefore, equation 2, v final equals v initial plus at. Substitute equation 2 into 1. Displacement is 1/2 bracket v initial plus at, close bracket, plus v initial, close bracket t. Multiplying that out, we get this equation. Displacement is v initial t plus 1/2 at squared. And note, don't have or need v final. So there'll be times when we don't ask for v final, don't give you v final. This is the equation you use. Displacement v initial t plus 1/2 at squared. Now, displacement when acceleration, initial velocity, time, and notice. Sorry, that's another typo. God bless microsquish. Displacement when acceleration, initial velocity, and time. No acceleration. I do apologize. And no v final. God help me. No v final. I'm sorry. Anyway, remember that these equations only work for concept. To save time typing, I used voice to text, and I didn't read it quite as carefully as I could have. Anyway, remember that these equations only work for constant acceleration. Now, a similar derivation leads to the formula displacements v final minus 1/2 at squared. Note the difference is subtraction sign, the fact we're using a final velocity now, and no v initial. All right. Now this is getting kind of long, so I'm going to pause it here. We'll do a couple of these questions. And yes, go ahead and laugh at my grammar and spelling. Anyway, any questions, shoot me an email. Otherwise, good luck.